All right. So, Mustafa, we are going to start, I think.
Yeah.
Okay.
I am
If you're
ready.
ready. So, today the first part of this thin film solar cells is going to be start with just the talk given by the Mustafa Kulakçı. Mustafa is just received his just master degrees or degrees in physics department from the Middle East Technical University. From the same university, he get just the master degrees. Following to the master degrees, he received the PhD degrees in 2012 on the implantation of the silicon nanostructure nanostructure in optoelectronics and the photovoltaic application. In 2013, he became a member of the physical department of the Eskişehir Technical University. Initially, it's known as Anadolu University. He has enlarged his research interest towards the epitaxial growth, fabrication, and characterization of 3 and 3.5 semiconductor devices. Recently, he has devoted much interest on gallium arsenide-based 3,5 group of thin film flexible solar cells. Today, he is going to make a talk. Is going to be given by the Mustafa Kulakçı is related with the gallium arsenide-based 3,5 thin film flexible solar cell by epitaxial of ELO technique. So, Mustafa, you can start because we have just 30 minutes.
Okay, thank you, Mr. Parlak. Welcome, everybody. My name is Mustafa Kulakçı from Eskişehir Technical University from Department of Physics. Today, my talk is based on actually a functional device concept, fabrication functional device concept for 3.5 solar cell structures, which is mostly used in space and some special applications only. So today I'm going to give some brief information about them, and I'm also going to give some short result of our work up to now in a few years, and also a new concept introduced by us, and there some pioneering results I'm going to share with you. So in the general outline, when we look, the general overview of the group 3.5 material system and some solar cell systems, and epitaxial lift-off method for cost reduction, which is important. Cost reduction is very important in 3.5 system, and search new pathway for maybe much cost-effective approach for the 3.5 flexible solar cell system, and then I give some brief conclusion to you. Okay, so the important group of material in technology today, you know, is 3.5 semiconductor system, sometimes called as boron or nitrogen group. When you look, when you look here, the most common group 3 elements are aluminum, gallium, indium in this system, and the others are in group 5, phosphor, nitrogen, arsenide, antimonide. Also, bismuth is important. It becomes as a new material in some new research topics. And the important thing is here, the sandwiched structure here, silicon, germanium, tin, and carbon is also very important in new shame device structure of group 3.5 materials. Group 3.5 materials are alloy compound from binary to pentanary now easily produced. And the important thing is here, you can do huge amount of engineering either inside of a band gap, you can easily tune by changing composition, and also there is a huge room for lattice constant. Lattice constant is very important for crystal growth technology, so you can play with lattice and band gap very easily. Also, when you look here, I'm not put gallium nitride-based structures, but there is a gallium nitride somewhere here, indium nitride somewhere here. They are also very important in optical technology, optoelectronic technology. Actually, silicon and germanium is also very important. Silicon is, you know, the horse of electronic industry, also photovoltaic industry. Today, there is a huge amount of search combine silicon with 3-5 technology. Actually, they up to now, by either bonding technique or mechanical stacking technique, very high efficiency solar cells are produced, either in 2-junction or 3-junction, which is comparable with the matured photovoltaic, 3-5 photovoltaic developed over germanium. So, what is the important thing is here, you can tune band gap of 3-5 compounds very easy shape, and you can cascade them in monolithic or non-monolithic structures into the template or high quality wafers. So when you look here over silicon in single junction, there's a huge amount of thermalization loss. Also, there's a huge amount of transparency loss. But in cascade structure, you can filter absorbed light over different solar cells junctions from high band gap to low band gap. Here, the well-known measured 3-junction solar cell or developed or germanium. When you look, you decrease thermalization loss as much as possible. Also, you decrease transparency loss by using germanium. Now, actually, by increasing the number of cascade layers to high band gap here, you can decrease thermalization loss much more again, or by changing low band gap material somewhere here, you also decrease the transparency loss, so you can utilize solar radiation in much better way. Okay, here there are actually 2 main solar cell technology in 3-5 system. One of them is upright, the other is inverted shapes, which means in upright structures, the solar devices are built from lowest band gap to the highest band gap. In inverted case, first you produce or grow higher band gap junction, then you grow lowest band gap, and then you just take this structure into the inverted shape in the normal structure of application, and then your solar cell becomes in normal structure in the use. But in conventional metamorphic structures, here inverted metamorphic structures, in conventional approach, you destroy this, dissolve out this gallium arsenide substrate, which means you lost your high quality crystal. But now, later I will talk, by using ELO method, you can also use this gallium arsenide by several, so you can decrease the cost of high quality crystals, okay? Actually, this ELO approximation in inverted metamorphic system, now Microlink and NREL collaborate, and they easily produce by using ELO structures instead of losing this gallium arsenide substrate. This is the main structure of conventional germanium-based multi-junction 3-5 solar cell, which is used in space application and concentrator applications, of course. Here you use germanium as a substrate, and you build your 3-junction over this substrate easily. This is well matured technology today and used in space from the middle of the 90s up to now. Okay, when you look, 3-5 solar cells are actually front runner in efficiency. The purples here are all 3-5 solar cells. Today, NREL reached 3-junction actually in monolithic shape, which is very difficult actually. So I think it is a miracle I see as a miracle today. There are three junction monolithic grown, and under concentration, which is concentration level is under 150 ratio, so it reached over 47%. In single sun illumination, this is around 39, but in under concentration, it reaches to almost close to 50 level of conversion efficiency. When you look here, all record efficiencies is of course belong to 35 groups, either single junction, of course, also multi-junction, either in single sun or either under concentrated level. All records are held by 35 group solar cells. You can easily see here from beginning to up to now. Of course, indefinitely you can make huge amount of junctions beyond 6 junction, but in practical case, it is not so easy. I think it is not also practical, or industrialization is also very difficult. So the main problem in 35 group solar cell is the device itself. It is very costly. Much of the cost is constituted by template or high quality wafers. When you look here, it is seen as 84%, but depending on technology, it can be changed between 80 to 90. So the price is very, of course, efficiency is very high, but price is also very high when compared with the silicon. At least two order price is included in the 35 technology. As far as I know, the 1 meter square is around $50,000 for high efficiency 35 solar cells. So these solar cells only used in some specific application. One of them is space. In space application, the important thing is watt per kilogram is very important. So 35 solar cell is match there. So price is not so important. Weight is very important there. In terrestrial use, CPV is concentrated photovoltaic system is very important. Actually, a decade ago, the concentrated photovoltaic looks like very promising in future projections, but today, concentrated PV is lost the race to the silicon technology. So the companies closed their facilities or almost finished today. In concentrated PV case, you just use a small area. Sorry, small area solar cell, which is very precious. Then you use some inexpensive lenses, then concentrate this huge area into the very small size. Then you increase the efficiency. Of course, by using concentrated light, in ideal case, current linearly increase, but you add up some logarithmic potential increase into the open circuit of the solar cell. Okay, when you look production tool, in industry, mostly used, actually there are two main production tools in industry for 35 devices. One of them is MOCVD system, metal organic chemical vapor deposition, or metal organic vapor phase deposition. In industry, this is very high output machines. Also, for high quality, you can use also molecular beam epitaxy system, but it is mostly used for some high-level other devices of 35 technology, or for research and development, you can use. Sometimes you should combine both. Some of the solar cell produced by, at some junction produced by MB, some junction produced by MOCVD. Also, there is a hybrid system, MOMBE, or some gas phase MB system. You can produce these devices. by atomic level control easily. When you look speed, growth speed, MOCVD is of course much higher compared to the MBE system today. Vico and show in an hour about more than 100 micrometer you can grow 35 metals onto the substrates. So the important thing is now the cost is very high, cannot affordable in terrestrial use, but there is a new technique. Actually, it goes back to up to 30 years. Epitaxy liftoff of these active devices, which is built on templates, then you can take out these thin active devices from the precious substrate, and you can transfer onto the flexible. It can be polyamide pad or metal foils, blah blah. Also, you can transfer onto the glass or silicon, whatever you like. In this shame, you grow devices on template, high quality template, by using some release layer. Then after growth, you can take out this release layer, and you attach these devices to the flexible plastics. In most common case, you use aluminum arsenide as a release layer. Then by using some special solution of HF, you can easily solve out aluminum arsenide, and your device is not affected with this solution. Then you can, after loss of aluminum arsenide, you can easily transfer these devices into the, when you look here, into the plastic carriers. When you look H ratio between aluminum arsenide and, for example, for aluminum arsenide, the ratio is more about 10 million times. Aluminum arsenide H rate is much higher when you compare to the aluminum arsenide. Aluminum arsenide is almost not affected in these processes. Here you see the general approach. Of course, there is some step is not included here. Only main steps are included. Of course, the device fabrication using epitaxy liftoff is very difficult compared to conventional case. First, you have to extract this active layer to the without any deterioration in the film structure, which is very single crystal over the substrate without any crack or any loss. Then you should transfer without any loss to the new carrier. When you look here, you first grow your devices, for example, for solar cells in inverted shape, which means the top junction is growth first, the last junction growth last. Then you deposit its metal back contact of the low energy junction. Then by using LO technique, you lift off, you just lift off these solar cells to the carrier. Then conventional device fabrication goes on. Here you have seen some projected substrate reuse. You can also use, of course, after liftoff process, you repolish your wafers, then insert into the, again, another sequential growth of solar cells. By using this way, you can repeatedly use this substrate, which makes a substantial decrease in the cost. Here you see there is some strategy. Actually, it is not, sometimes it is not realistic for me. In 10 times use, 20 times use, 50 times use, and 100 times use, you can easily, with chemical mechanical polishing, with mechanical polishing or without mechanical polishing, you see the substrate cost for, actually this is for 6-inch substrate, and they assumed at the beginning the substrate price is $150, but it is not realistic. Of course, maybe in huge production it can be realistic in future, but today it is not realistic. Also, alpha devices confirm 10 times use of gallium arsenide substrate without any change in sequential device processing. There's no change in efficiency in the devices. Of course, by decreasing this device cost, you can also rebuild concentrated photovoltaic. Instead of high concentration ratio, you can only build some low concentrators between a ratio of 10 and 15, and you can also decrease cost moreover these guys 10 times maybe or more. Here you see how the picture of lift off to solar cell structures. Actually, you can apply a LO structure from micrometer square to up to full 6-inch. Actually, in 6-inch, maybe there can be problem in this case in industrial case, but up to 6-inch you can easily grow. The left-hand side, these are belongs to us. One of them is laminated structure on the PET carrier. The other is attachment to the flexible polyamide by using gold fusion techniques. Here you see this is again from our labs. Full 3-inch solar cell structure is lift up from substrate into the PET carrier. Okay, so by new approximation, you make, of course, beyond the cost decrease, you also insert huge amount of functionality of your devices. One of them is lightweight. The panels are 1 meter square panel are sorry. A panels with 1 meter square is less than 500 grams, actually between 200 grams and 500 grams, depending on carrier and junction type of your devices. High efficiency, today one junction solar cell is around in gallium arsenide around 29%. Also, microlinks inserted about 38% inverted LO process with 3-junction. It is flexible. The flexibility is the radius of curvature is about 1 point in radius, 1.5 centimeter in radius. Of course, you can build very, very thinner or ultra thinner devices. The devices with only 2 nanometer thickness proven by researcher with an about efficiency close to 20%. Of course, you can room for up to 100 nanometer, but of course, maybe you need some special texturing in the front side of your devices. When you look here, this is the NASA ROSA project. There is a rollable solar cell. Then on space, it is opened from the roll, and now NASA going to increase the design or change it in different way by using these devices. Also, in aerospace side, it is very important. This is the from Zipper project of Airbus, collaborate with Microlink, and these UAV systems are used in high altitude system for as a potential satellites. Of course, in terrestrial application, you can also use in every case by decreasing of cost. But when you look actually the customer is mostly the army side and also space side. Okay. So I'm going to give some slides about our research. We also a newcomer into this site. We also produces flexible solar cells by using LO structures. This is the main shame of LO cells. When you look, the absorber layer is half of. Sorry, it should be one. There's a mistake. It is half of the real wafer-based conventional solar cells, but in a simulation, the thin film is a bit 2% higher compared to the wafer-based case, but in of course, in our facilities, there is some deterioration in the thin film yellow cases, but the realistic case, when you look, the efficiency is a bit, not a bit, much lower compared to the conventional cells. Here you see the conventional cell efficiency at the highest efficiency is about 22 for p-emitter structure. It is about 20, almost close to 21 and a half in an emitter. For the case in LO cells, the highest efficiency we get around 90%, and for p-emitter, and around 90 and a half for an emitter. Of course, in design and simulation case, it was opposite, which means an emitter is much higher compared to p-emitter, but after production, we see opposite. Most probably those are due to production change in our laboratory. When you look in conventional cells, actually there is no shunt loss. The loss are all related with series resistance, but in LO cells, there is a huge amount of shunt loss. Also, same way, there is a huge amount of series resistance loss. When you look fill factor, actually, in realistic case, it should be around 85 or more than 85, but due to series resistance, it decreased to about much lower than 80%. Also, the metal shadow is a bit higher. It should be decreased almost half of it. Then in projected case, it can reach about 27%, maybe, if you make better contact shape. Of course, these contacts here are very thin. Actually, it needs electroplating much more over it, but we have no infrastructure to do that. Same things also holds for LO cells. Okay.
5 minutes.
Okay, I am going to finish rapidly. Here, we are looking to decrease the substrate cost much more over conventional LO cells. So we conducted research on heteroepitaxial over silicon substrate first time. So I am not put all details here due to patent concept, and also this is the first time announced to anybody here. So instead of gallium arsenide template, using much cheaper silicon, actually, when you compare with gallium arsenide at silicon price, the cost is increased up to 1,000 times when you reach to the 8-inch full substrate size. Of course, gallium arsenide also at each technology is now at 8-inch, but it is not matured yet at very high prices. So we think that maybe it can be lift off from silicon templates, but there is an obstacle, of course. One of them is polar material, the other is non-polar. There is a 4% lattice mismatch. Also, thermal expansions are very different between them. But when you look in general perspective, gallium arsenide, of course, reusable by using LO technique, and it, of course, high quality for epitaxial growth, but silicon is very cheaper. It can be reusable when you compare much more times when you use, compare to the silicon, gallium arsenide actually, but you need very high quality dislocation filter. Otherwise, you end up with defective structures, which kills your devices. So, in the research at the beginning, the important thing is what kind of defect filters or dislocation filters we should use to confine this treating dislocation don't reach to the active device cells. So we have used actually 4 shapes. One of them is periodic quantum dot arrays between 5 and 10 periods. Also strained superlattices and mix of superlattice and quantum dot arrays. But at the end, we end up with the high quality we reach by step growth in thermal cycle, which means some of the dislocation filter layers is produced in different growth temperature, then goes to the thermal cycle at high level, then go back to the another growth step, blah, blah. Here you see these wafers are grown on 100 silicon wafers, but it end up with anti-phase domains here, like a multicrystalline silicon solar cell due to gallium anti-site bonding between gallium and arsenide and arsenide level. But change the template to miscut template, off-cut template from 100 and 4 degrees, we prevent this APD formation. Here you see our two of the growth structure over 2-inch silicon and 4-inch silicon. It's just like a mirror-like reflectivity over the surface. Okay, when you look at the measurements, both racking curve at the left-hand side and the omega-2 theta secant at the right-hand side, you see gallium arsenide 004 plane and silicon here as a 0 plane. And the best achieved results in structural case is about in full width at maximum is about 150 arc second. And also when you calculate TD dislocation density, it is lower than 10 to 6 per centimeter square. Actually, in this calculation, of course, we have to also include the buffer layer, which means that our active solar structure defect density, tilting dislocation density, should be much lower than this guy. When you look to the PL results, here you can easily see the efficient PL emission from the devices over silicon. And also, when you compare with gallium arsenide, of course, a bit lower compared to the gallium arsenide reference, but we are going to, maybe in a week, we are going to almost reach to the gallium arsenide reference case here. Of course, these are the first solar cell alloy structures transferred directly from silicon in the world up to our knowledge, and it is first announced also here. Here you see the picture of some lift-off and transferred solar cell structure by using lamination method, and here you also see by using a fusion method to do Pvcon polyamide carriers. Okay, after, of course, after epitaxy or liftoff from silicon, we also measure the PL of these geysers. When you look, actually, the front side of quality is seems a bit lower compared to the backside, but when you look, same things also holds on gallium arsenide wafer. Also, the important thing is here, you can easily see valence band splitting. Here, this is the degeneracy is broken in the valence band. This is a light hole and this is heavy hole, which means due to tensile strain over the surface of devices, the band gap shifts to lower energy, and also in some cases, depending on the strain on the devices, you can easily see the valence band splitting, which can be also maybe utilized for any strain measurement sensor applications maybe. Well, and this is the first alloy fabricated again or silicon gallium arsenide solar cell. Here you see the external quantum efficient measurement. Actually, these are the first fabricate devices. I am just put this guy. The later is due to again patent issues. I'm not put here. This is the external quantum efficiency. The green one is directly lift off from silicon substrate. The red one is the reference one, solar cell over gallium arsenide. When you look, there is a loss in infrared region due to defects, which means the diffusion length is not enough to take out the carriers from the backside of devices. But depending on this, guys, we change device design, and nowadays we are going to produce these devices, and maybe in future we are going to publish in a high quality journals. So in conclusion, there are two main conclusions here. One of them is epitaxy liftoff method is very effective for cost reduction for very functional devices, which means open a new route to the TLU5 solar cells. I guess that in future, all TLU5 solar cells is converted to the epitaxy allo cell process, I think. And also the pioneering results shows that the production also may be possible over silicon for a substantial increase in the cost of these devices. I want to acknowledge my students. Also, I want to applaud TÜBİTAK and Eskişehir Technical University for support for the research of these projects. Okay, thanks you listening.
All right. Thank you very much, Mustafa. So it's your nice presentation. So I would like to ask the audience, do you have any question? Let me ask first of all, because maybe my first question is going to be related with the gallium arsenide thickness before just etching for those invert structure.
Sorry?
I'm asking just the gallium arsenide thickness before starting
it is around 450 nanometers. The substrate or film side?
Substrate.
Yeah, it is around 40 and 50 micrometer.
50 micrometer.
Yeah,
because
close to half millimeter.
What about the thin films case?
In thin film case, the device is including all, in our cases, about just below 2 micron. And you can, of course, we also produce devices about 1 micron thickness.
I see. So there is another question, because this is the second question. We are talking about the concentrated solar cell.
Yeah.
What about the size of that solar cells if you are using the gallium arsenide? Because there should be just optimum size, I think. So that to provide
Actually, it depends on concentration ratio. If you have to use high concentration ratio of several hundreds, of course, it should be very small, maybe millimeter squares. But in low concentration case, maybe 10 or around 10, it can be big compared to the high concentration.
Size of, yeah.
Yeah.
All right. Is there any questions? At the moment, you can easily be just cost can be submitted, Mustafa. There are 3 dots.
Yeah, I'll just stop share now. Then, which one I'm going to give assignment to? I'm just looking for. What was the name of company?
Parmatic, yeah.
Digital. So Parmatic Digital. I couldn't see Parmatic. Sorry for that. Is Parmatic.
It's seen after me.
Yeah, I can see. So May cost.
All right.
Yes. Okay. Thank you all.
Okay, thank you very much, Mustafa, again. So take care and see you later. All right. Bye.
See you.
The next speaker for our case is going to be the Ceren Korkut. Ceren is she is a master degree in physics department of the Middle East Technical University. Following to the BCS degree, she is a member of just start just the master degrees. So at the moment, she's a member of the nano-optic research group. So today she is going to be giving a talk about the laser crystallization of the alpha germanium thin film by nanosecond pulse infrared laser.
Good morning, everyone. My presentation is pre-recording.
Good morning, everyone. My name is Ceren Korkut. I am a master's student in physics department at Middle East Technical University, and I am a member of nano-optics research group. Today, I would like to talk about laser crystallization of amorph germanium thin film via nanosecond pulse infrared laser. Let me start with our motivation. Germanium and silicon are frequently used semiconductors in solar cell technology and photovoltaic application. Germanium is expected to be a promising material for next generation thin film transistors because of its high carrier mobility, low contact resistance, and optical bandgap energy compared with silicon. Crystallized semiconductors are best performing materials in photovoltaic application, electronic sensor industry due to their superior electrical and optical properties compared to their amorph counterparts. Forming highly crystallized semiconductor thin films on glass substrate offers to improve low efficiency, low cost amorph materials that are used in solar cell technology. Different techniques have been applied in order to produce polycrystalline germanium films, such as solid phase crystallization, metal-induced crystallization processes. Unlike all the traditional techniques and thermal processing, pulse laser processing offers versatile control on the phase transition of the material from amorph to crystal in short duration. The main advantage of the laser crystallization is to adjust the rapid cooling by changing the overlap ratio of the successive laser pulses. Nanosecond pulse laser provides more heat accumulation on the surface, and the crystalline grain domains were aligned by sustaining heat accumulation over the film. Controllable the geometry of laser spots deliver the benefit of avoiding random nucleation so that intended crystalline structures can be projected over the film. Unlike the spot focus scanning, the size of individual polycrystalline germanium domains can be increased by a line focus scanning. In this study, our aim is to produce high-quality crystalline samples that can be grown in a short duration. And secondly, to describe nanosecond infrared laser-based crystallization process of germanium by implementing suitable laser parameters to fabricate thin film devices. Our last aim is to minimize the thermal budget of the crystallization processing and provide flexibility to locally crystallize thin film. Let me give you brief basics of laser crystallization. And the laser crystallization process via nanosecond pulse infrared laser is initiated with the melting of the amorph germanium film by absorption of infrared irradiation. The interaction between thin film and irradiation initiates with the generation of free carriers and phonons through absorption of light by valence electrons, where electron-hole pairs recombine through non-radiative recombination and transfer the energy to the bulk atoms in the form of heat. When laser crystallization is performed, Explosive crystallization occurs as an intermediate effect. The free energy realized during crystallization is used first to sustain crystallization on the surface, secondly to locally heat up substrates. In this experiment, amorphous germanium film with a thickness of 300 nanometer has been deposited on glass substrate using E-beam evaporation technique. The amorphous germanium film was crystallized using nanosecond pulse infrared laser at room temperature in air. A nanosecond pulse infrared laser with a pulse duration of 200 nanoseconds and a repetition rate of 100 kHz at the wavelength of 1064 nanometer was employed. And the scaled microscope image and corresponding electron backscatter diffraction maps of LC regions are seen. With a low laser fluence under laser crystallization condition, pinhole formation in the germanium film can be easily seen. Besides pinhole formation, the radial extension of germanium has been observed, which is centered around the defect during melting and crystallization of amorphous germanium. This indicates the explosive crystallization phenomena. Defect formation and damage of the film can be avoided with an optimized laser fluence of 110 millijoule per centimeter square. And we used overlapping factor to get large crystallized area. Microstructures start from a random nucleus with a single pulse and extend radially outwards, generating fan-like microcrystal domains with different orientation. To get much knowledge about the sample morphologies, laser crystallized regions were analyzed with scanning electron microscope, SEM. For the sample process with a laser fluence 115 millijoule per centimeter square, structural deformation is clearly visible as a large crater and heterogeneously defective region formation in picture A. On the other hand, inconsistent with optical image, the sample process with 110 millijoule per centimeter square shows homogeneously and smoother surface morphology after the crystallization process. And Raman shift of crystallized germanium and bulk crystal germanium are compared. And Raman shift of crystallized germanium is very close to Raman shift of bulk crystal germanium. And in order to determine the optimized laser fluence, we scan sample with different laser fluences. And for laser fluence lower than 110 millijoule per centimeter square, the line width of Raman shift gets larger because of number of defects, high density of defects or crystalline size. There is a redshift in Raman peaks, which is attributed to the tensile stress on the film. And above the 110 millijoule per centimeter square, we observe damage on the surface. That's why we choose 110 millijoule per centimeter laser fluence. Then the value of scan speed was changed to control the overlapping factor. To understand the effects of overlapping factor, we change scan speed with a fixed laser fluence were examined. And above the scan speed of 30 millimeters per second, there is no sign of crystallization. And between 5 and 30 millimeter per second, we observe damage and defects on the surface. That's why we choose laser fluences of 110 millijoule per centimeter square and scan speed of 5 millimeter per second. And X-ray diffraction spectrum of sample irradiated with a laser fluence of 110 millijoule per centimeter square with 5 millimeter per second scan speed. The diffraction peak of the laser crystallization germanium is mostly oriented to the 2 to 0 peak direction, which indicates microcrystal germanium domains. The film is preferentially oriented to the 2 to 0 direction. As a conclusion, in this study, we achieved to process the germanium ultra-thin film in a controlled manner via nanosecond pulsed infrared laser. The nanosecond pulsed infrared laser creates microcrystals which have a average size of 10 micrometer on the 300 nanometer thick amorph germanium on glass at room temperature. This study introduced micro polycrystalline germanium demonstrates the laser crystallization of 300 nanometer thick amorph germanium via nanosecond pulse infrared laser and provides new device application of photovoltaic technology and thin film transistors. The most suitable crystals were obtained by using the nanosecond pulse infrared laser with aspect ratio of 30 to 1, and it provides the production of ultra-thin film crystal germanium films for device application which are subject of further research. Thank you for your listening. This is the end of my presentation.
So, Ceren, thank you very much for your nice and short presentation because we have a time. So, in any way, let me use that time for the questions. So, let me ask the audience, do you have any questions? So let me ask the question, because in the first part of your talk, you are just talking about the low contact resistance of the just alpha germanium. What does it mean with the low contact resistance? Because that depends on the what? That depends on which kind of material you are going to use as a contact materials, I think. So you are saying the low contact resistance means what? You are talking about the, I think, general resistance, is it?
Yes, yes, right. And we are at this in this study we are using glass substrate, and we amorph germanium film deposit on glass substrate, and it's so lost cost material. Glass substrate is low cost material, and that's why I say low
Contact, you mean?
yes, sorry, I'm so excited.
All right. So that, as I told you, yes, that depends on which kind of the material you are going to be used as a what to make a contact with the other materials. So the germanium is the low resistive materials, depends on the what? Depends on the what? Carriers, I think, which kind of the carriers and the binding energies. And you say that there is a photon energy to obtain the thermal generation of free carriers.
Yes.
What about that energy?
Actually, this interaction between film and light starts with the generation of free charge carriers and phonons. And these free charge carriers and phonons, through absorption of light by valence electrons, and where electron hole pairs recombine through non-radiative recombination, and this energy transfer to the bulk atoms in the form of heat. And this heat provides melting of amorphous germanium
So
layers.
what about that values? That is just the 10 or 20? I think that's also depends on the binding energies, isn't it?
Yes, and this energy is very close to melting temperature of amorphous germanium, and then amorphous germanium liquefies, and then crystallization domains occur.
So again, I would like to thank, if you don't have any question about our audience. So there seems to be no question. Again, Ceren, thank you very much
Thank you.
to you. All right. So the next speaker is going to be Hazal Gündoğan Kurtlu from the İzmir Institute of Technologies. He's going to be just tell about or to talk about the effect of the argon gas flow rate on the growth structure and the optical properties of the sputtered antimony selenide 3 absorber thin films for solar cell applications. So yes, Ceren, Hazal, sorry. It's your turn now. Hazal, are you? I think, yeah.
Hello, I'm Hazal, joining from İSTEK İzmir Institute of Technology. Actually, I'm doing my master education in energy engineering department. And let's start today. I will present my presentation with the title, The Effect of Argon Gas Rate on the Structure of Magnetron Sputtered Antimony Selenide Thin Films. Pardon. Okay, this is my outline. First of all, I will talk about why thin film solar cells are drawing attention. What are their advantages over crystalline silicon solar cells? And what is the status of antimony selenide? Why did I choose this material? What are the advantages compared to other commonly used semiconductor materials in thin film solar cell technology? And after results and discussion part, and finally, conclusion. Okay. Why thin film solar cells are important? Because if we compare with the silicon technology, thin film solar cell technology have low cost for production, and deposition of semiconductor materials onto a substrate, and finally thin film solar cells occurring, and thicknesses varies from nanometers to micrometers. They are flexible. For example, crystalline silicon solar cells are very rigid and very high weighted, so and they are not flexible. And the most important thing in thin film solar cells, material have direct bandgap energy, but in crystalline silicon solar cells, they have indirect bandgap energy. And crystalline silicon solar cells needs very thick layer to absorb the incident sunlight, but thin film solar cells have very high absorption coefficient, and these are the advantages over crystalline silicon solar cells. And why antimony selenide material instead of other commercially used CIGS, cadmium telluride, CZTS, they are more popular. Actually, antimony selenide compound is a two-component basic P-type semiconductor. The CIGS, copper indium gallium diselenide, cadmium telluride, CIS, these are commercially take part as an absorber layer in the thin film solar cell production, but cadmium is very toxic, and indium, tellur material are very expensive due to their limited underground reserves, and it's very costly to make them usable. But antimony and selenium, these two materials, contains abundant elements in the nature, and they are low cost, affordable cost. They are non-toxic, this is important, and they have high absorption. This material, this compound, antimony selenite, has high absorption coefficient, greater than 10 to 5%, and the band gap is favorable between 1.1 electron volt to 1.3 electron volt. Here we see the graph taken from the Shockley and Kessler. As we know, in PV photovoltaic technology, optical property of the semiconductor material, the material used in the stack order as a P-type material, is very significant to obtain high efficiency. And here we see the antimony selenide maximum theoretical efficiency calculated as 31.7%. It's really great. Yeah, here we see the article with the high efficient until now, 9.2% antimony selenide solar cell. And actually, if we look a little to the history of antimony selenide material, it's firstly explored by Nair and his research group in the beginning of 2000s as an application of photovoltaic device. But of course, yielding a rather low conversion efficiency like 0.66%. And until now, so we can say it's been 20 years, the studies going on antimony selenide, verified record power conversion efficiency 9.2% for antimony selenide solar cells is reached by Lee and his research group in 2019. And here they claim that how did they reach this highest efficiency? They applied the interface engineering with titanium oxide material. Here you see this is P-type absorber layer in solar cell stacking order. This cadmium as cadmium sulfide is N-type buffer layer. They brought titanium oxide compound between P and N-type layer to prevent the antimony migrating to cadmium sulfide layer. So until now, they reached the highest efficiency. Yes, now aim of this study. In this study, antimony selenide films have been grown with radio frequency RF magnetron sputtering method onto soda lime glass substrate with different argon gas rays. To different argon gas rays, morphological, structural, and optical properties of antimony selenide thin films were systematically investigated as a function of the pressure. And in this picture, you can see the sample I grow on soda lime glass. As you see, the color of the antimony selenide target is dark gray and it looks like metallic. Okay, going on. And here, yeah, we see the table with 6 samples I have grown, and we see the table with the parameters of the samples I have. Yes, in this study, antimony selenide absorber layers, I've already said, grown with RF magnetron sputtering method by using different argon gas rate. Here, starting from 20 SCM until 50 SCM. This argon gas flow rate, of course, affect the pressure in the sputter chamber, affecting the pressure. So hereby the optimum pressure for the coating adhesion and structural properties were determined. And in addition, the effects of the argon gas rate on the physical and the optical properties have been investigated for use in thin film solar cells. Yeah, now we see the annealing process graphic, and why we applied this annealing process. because because of the low mobility of antimony and selenium, these two element atoms, the antimony selenide thin films grown at room temperature are amorphous. So we therefore applied heat treatment to all 6 samples, but parameters are same. The samples annealed at 350 centigrade degrees for 30 minutes under 100 SCM argon gas flow, and ramping rate kept stable at 20 centigrade degrees per minute. Yes, now results and discussion part. I will talk about thickness measurements, XRD, Raman analysis, SEM and EDX analysis, and finally optical analysis. Here we see the thickness measurement graph. You see it looks like an unstable graph because until 35 SCM, thickness increased up to 30 points regularly, but the thickness was unstable above 30 SCM. For 40, 45, and 50 SCM, thickness is not stable. Actually, this is very similar with the Nishat Arshis group study, because they also found the similar results as an unstable thickness with respect to the argon gas flow rate with titanium nitride films. So we can say that gas pressure, argon flow rate affects the thickness, but it doesn't look like a regular in this graph. But according to the other studies, for example, Musab Salman Sultan studies, he also studied the effect of argon gas rate on his devices. There is a slight, according to him, there is a slight reduction in the deposition rate by increasing the gas pressure. And thus, the thickness decreases with increasing the argon gas rate. And this was, he attributed this to the collisions enhancement among the ejected particles, or the reduction in the thermal energy of the sputtered atoms from the substrate. But of course, we cannot say thickness changes the structural property of the material. It doesn't affect any structural property of the antimony selenide absorber layers. Now we see the 6 graphs of XRD analysis results. First, I want to talk about a little bit the crystalline structure of this material, this compound, antimony selenide. The binary compound antimony selenide has an orthorhombic crystal structure, which belongs to the space group PNMA 62. To improve the performance of the solar cells, the control of the crystal orientation of antimony selenide film is a key factor. But it's valid for all other semiconductor materials used in solar cell technology. To crystalline, to see these peaks in XRD result, I've already previously, I've told that we applied heat treatment to all 6 samples. If we didn't apply this heat treatment, we couldn't see these XRD peaks in the analysis. And here you see there's all peaks corresponding to the antimony selenide characteristic peaks, but you see in 211 observed at 28.2 degree and 221 31.2 belong to the lattice planes 211 and 221 orientations. These orientations are important for the quality of the diode. The 221 orientation allows better carrier transmission within the antimony selenide film and also allows less defect occurrence at the interface, which explains the improved diode quality and device performance. Therefore, in our study, the intensity of the peaks with the orientation 211, so HK1 and 221 orientation were used as an indicator parameter for the quality of antimony selenide films. Regarding these orientations, when we analyzed 6 graphs, the sample grown with 25 SECM argon has reached the best results. You see other samples. For example, if we look at the sample grown with 45 SECM argon, the HK0 planes orientations are dominant. And these dots shows antimony oxide phases. Here you see dot. And the dots exist in the samples grown above 30 SECM and above. Let's continue. Here, this is the texture coefficient of diffraction peaks in the samples with different argon pressures, starting from 20 SECM to 50 SECM. You see, these are the indicator. I have told that 211 and 221 orientations will be used as an indicator parameter to understand the quality of the film. And here the red one, so 25 SECM, have the highest value for these orientations. Yes, Raman analysis. Raman XRD analysis is not enough for by itself. Raman analysis results should have support XRD analysis. Here we see 2 graphs. First one is antimony selenide region. Second one is oxide phase region, high frequency region. Raman analyzes, Raman spectroscopy utilizes vibration peaks of the elements, different from XRD. So we see
just 2 minutes, all right?
the films which I have grown using 40 SECM argon and above. Oxide phase were observed. Here
Azal,
you see
2 more minutes.
264 and 451.
Yes, I hear. But my presentation takes much more time. A few minutes more.
I'm sorry, but we have a time because there is a other scheduled person, so he is waiting.
I see. Okay.
2 more minutes, all right?
Then, okay, we can go to conclusion part.
All right. So who is it, that person? Just make an introduction. Hazal just is, you are not connected, I think, are you?
Yo, can you hear me?
I'm hearing you, but the presentation doing by the other person. Who is the name of?
I think I'm connected because I can see the presentation.
I see it. I see also, but the person with the sunglasses, the girl sunglasses, are you?
No.
Who is she then?
I don't have sunglasses. I have orange jacket.
No, in any way, just let's continue, all right?
Okay.
If we look at the first graph, all films have characteristic peaks of the antimony selenide structure at 209 and 252 points. This 209 point originates from the vibration mode of antimony and selenium, and the other 253 peak is originating from vibration mode of selenium ring, selenium atom. Yes, now SEM analysis of antimony selenide samples. Here we see the 6 samples images. When we look at all these images, the grain boundaries appeared more clear in samples grown under pressure 35 SCCM argon. The peaks observed in XRD also assigned to the granular structure. The grain structure is of great importance in solar cells. The grain boundaries serve as the junction center, recombination center for electron hole pairs, and it affects the open circuit voltage of the solar cells, and open circuit voltage is affecting the efficiency of the device. It's significant. And when we look at the 40, 45 and 50 SCCM images, we see extraordinary images showed up at these samples. And it can be attributed to selenium separation from the film surface and gap formation. Because at the higher argon gas rates from the sample's surface, selenium separating. And here at the left side picture from Zhang's article, we see the morphological image of the oxide, antimony oxide, and the other is our image taken from the 45 SCM argon sample. When we close up to the image with the sample 45 SCM argon, we have taken the point EDX analysis from spectrum 8. This bright crystalline structure belongs to the antimony oxide compound. EDX results shows that it's detected by point EDX analysis. And this case can be explained by the decrease in the selenium ratio, which is not desirable for antimony selenite compound in photovoltaic applications. Because selenium separate from the film surface during the sputtering at higher argon gas rates.
Let's come to the
Finally,
result.
optical analysis. We see transmittance as a function of the wavelength graph and optical bandgap energy values. The transmission graphs of the films are different from each other in the visible.
Hazal,
You see in the visible
come
region,
to the conclusion, all right?
500 nanometer between 800
okay.
nanometer.
All right.
Now can you see me?
Yeah, I'm seeing you.
Okay, no problem.
But there is a presenter, so presenter has what glasses, so that glasses is different from you. I think you, in any way.
Okay.
I think you are conclusion, is it? Okay.
Can I control the slides? Because now I can't control. If we can jump to the conclusion part. Here we see the optical analysis of antimony selenite samples. And the next slide will show the band gap values. I have to see the slide.
I see. So you can easily pass the other sides because you can easily just, I think you just place the video of your studies. So you have to just maybe summarize the conclusion period, all right? Without using that video.
Okay.
All right.
Okay, sorry, excuse. Can you wait just a second? Because I have to open the slide. Okay. Abi dondu ya. Hayır, açık şu an. Dondu bilgisayar.
Sana soru soracaklar mı?
İşte sorduk, conclusion'a gelirse.
And
Bilgisayar çalışır.
convolved. But as you see with the other samples, which we detected oxide phase in XRD, in Raman, and SEM analysis, their band gap energy is very high and it's not preferable. So to conclude, in this study, RF magnetosputtering method was successfully used to fabricate antimony selenide thin films for solar cell applications. All samples have orthorhombic crystalline structure. The sample grown with 25 SCM had the best result in terms of the crystal structure. The oxide phase antimony oxide was observed in the samples grown with 40 SCM and above. The energy band gap values of antimony selenide films were increased with the argon flow rate. So with this study, we show that argon gas flow rate can be a parameter to obtain good quality antimony selenide films as an absorber layer. And finally, acknowledgement. This research is supported by TÜBİTAK project number 118 F143, and this study was partially supported by Scientific Research Coordination Unit of Pamukkale University under the project number of HZDP041. And thank you very much for listening to me.
So I'm asking the audience, do you have any questions? So it seems to be there is no question at the time being. So in any way, just pass through the other speaker. Thank you again, Hazal. Thank
You're
you very
welcome.
much. All right,
Thank
bye.
you too. Bye.
Bye. See you.
See you.
The next speaker is the Teoman Özdal from Çukurova Universities. He had got the PhD degree from the Çukurova University Physics Department. And he's going to be just relate with the low-cost solution-based zinc oxide, copper oxide heterostructure for photovoltaic applications. All right, Teoman?
Unfortunately, Teoman has to be out, and he records the talk, and we will follow it for him.
All right, okay. In any way, we are going to listen then.
Okay, thank you.
All right, bye.
Hello everyone, this is Teoman. First of all, I want to thank Pvcon 2020 organizers for this very useful conference and their valuable efforts. Title of our presentation is Low-Cost Solution-Based Zinc Oxide Cuprous Oxide Heterostructures for Photovoltaic Applications. The main subject of this presentation is the optimization of our previous zinc oxide cuprous oxide solar cell device study, which is recently published. Here, we focused on the zinc oxide transparent conductive oxide layer to increase the device efficiency. We can list the motivation as follows: band gap, exciting binding energy, abundancy, and toxicity, and usefulness of zinc oxide in optoelectronic applications. The zinc oxide's bandwidth allows its thin film to transmit spectrum from ultraviolet to near infrared, which covers close to 19% of the energy. It is perfect Windows material for visible spectrum applications, such as solar cells, diets, etc. The high exciton binding energy makes zinc oxide useful in optoelectronic applications at room temperature. It's very important. Its stability at room temperature makes zinc oxide very useful for optoelectronics used in applications in our daily life. Zinc is also naturally abundant and relatively inexpensive material. That is why zinc oxide is highly preferable material for low-cost optoelectronic applications. Here we can three types of elements. You can see three types of elements here. Major industrial metals in red, which is zinc involved. Precious metals in purple, and rare elements in blue. The zinc oxide semiconductor can remain in good condition for months, and even its crystal structure improves over time. Here, with the penetration of oxygen into the zinc oxide semiconductor over time, the structure showed better crystallinity, and therefore its conductivity in the visible region increased further. Its green emission decreased over time because of the penetration of oxygen. Here, as deposited, we can see green emission around 500 nanometers here. After 4 months, oxygen penetration makes the emission lesser, and after 6 months, the zinc oxide is very optical ideal for visible region. Near-band emission, by the way, near-band emission increases over time. Here, we can list the outlines as follows. Deposition of zinc oxide thin film layer, comprehensive analysis of the results, deposition of cuprous oxide thin film layer onto zinc oxide, characterization of zinc oxide, cuprous oxide solar cell device, and conclusion. Our talented collaborator Merhan, aka Magic Hand, optimized the deposition of zinc oxide thin film. We thank her. She first increased the amount of stabilizer monoethylamine in the solution. She also heated the solution before the spin coating, and then voila. Her optimization of chemical ratios in the solution and exothermal treatments before and after the deposition made this work possible. Here we can see why we call her the Magic Hand. The left diffractogram is from our previous work. The right one is from our last work. Both films were spin coated on glass substrate for 6 times with the same parameters. The crystallinity of zinc oxide has increased in tens of thousands of times. Moreover, only along the 002 plane, thanks to her, we have achieved a much better zinc oxide structure. As can be seen from the optical transmittance results, better transparent conductive oxide thin film was obtained. The new zinc oxide film gives an interference pattern indicating an increased crystallinity. Here, zinc oxide films were 10 times spin coated on ITO substrate for the solar cell device application. The intensity of the pure zinc oxide is around 20,000. The crystallinity of the N-doped, nitrogen-doped film has decreased considerably. We can say that nitrogen doping successfully fills the zinc vacancies in the crystal. Although the crystallinity of aluminum-doped films is relatively lower, it is still only 002 plane oriented. As the aluminum ratio increased, the intensity of crystallinity decreased. Since the zinc ratio that participates in the crystal structure in the film is low, the crystallinity decreases as the aluminum ratio in the crystal increases. However, optical properties were obtained close to each other, except for the end-doped sample. The optical transmittance of the end-doped sample in the UV region is less than one the others. All the films gave an interference pattern. As can be seen from the SEM image, both pure and nitrogen-doped zinc oxide films are homogeneous. There are no cracks and pinholes on the surface of the films. The particle size of the pure zinc oxide thin film is larger, and its thickness is around 210 nanometers. The particle size of nitrogen-doped zinc oxide film is small, and its thickness around 30 nanometers. We electrodeposited cuprous oxide layer onto zinc oxide with two electrochemical cells at 0.9 milliampere to centimeter square constant current. We used a simple DC power supply as current source and microammeter for manual controlled current density. Platinum sheet was used as counter electrode. Here is the cell, power supply, and microammeter. Same image shows cuprous oxide surface and cross-section of our zinc oxide cuprous oxide device. The cubic structure of cuprous oxide can be seen from the surface image. Here we can see the cubic structures. Zinc oxide, cuprous oxide. The thickness of the cuprous oxide was about 2.2 micrometers here. Here we can see schematic and actual image of our solar cell device. Our cell fabricated onto 2.5 centimeter square glass ITO substrate. The heterojunction divided into squares, and then silver paste applied to create top and back ohmic contacts. Here, schematic islands, and here, the actual islands. By dividing the cell surface into islands, we can obtain individual IV characteristics from different parts of the device. Here we can see 12 different islands, separated, and they have common back contact here, and individual top contacts, silver contacts here. Unfortunately, we have not been able to characterize the solar cell device with pure zinc oxide, as we have not yet completed it. Anyway, our champion device is the device fabricated with nitrogen-doped zinc oxide window layer. The output current and voltage is still low, but now we know that the device efficiency can be increased by focusing every part of the device carefully. Nitrogen doping exhibited better results than aluminum doping. Increasing the aluminum doping decreases device performance. Here, increasing aluminum doping, decreasing efficiency. Here, we can compare our recent results with our previous work. This comparison is still quite meaningful, also not with the device with pure zinc oxide. Because the increase in filling factor and output voltage indicates that we have produced a better interface. Increase in the filling factor showed that we have better interface because of better crystal match between zinc oxide and cuprous oxide. Output voltage and current also increased around 3 times. These results are achieved with simple parameter optimizations in the spin coating process of zinc oxide. In conclusion, we first say that the solubility of zinc precursor in the solvent is the K factor of zinc oxide crystallinity. And the nitrogen doping is another good effect on the device efficiency. Our future work will be focused on the interface. We are planning to apply surface treatment on zinc oxide layer and add extra intrinsic layer between zinc oxide and cuprous oxide. Thank you.
All right, thank you very much, Teoman, but I couldn't say the thank you because your teacher is over there, so I would like to thank to you, all right? Hava Hanım, IT? Your microphone is closed. You can open the microphone.
I already opened.
Okay.
Okay, sorry about that. He has to go to the school and he has his teacher and they called him to go to the school. That's why he has a problem to connect and
I see.
we can answer the question.
All right. So at the moment, because I think you did this study together, isn't it?
Yes, and Merham, she's here. She made the zinc oxide very good. I mean, very, very good. Just 002 and very intense speed with Soljan, with the speaker.
In any way, let me ask the audience. Do you have any questions?
Okay.
I think nobody says, yes, I have a question, but at the moment, let me ask the question as usual. Thermal treatments, and we are talking about thermal treatments for the what? For the just zinc oxide and the azo case. The concentration and the thermal treatment or the thermal substrate temperature is going to be changed as a function of time, I think. And they depend on the concentration, isn't it? So which one is important as you are talking about the XRD studies? Because in the XRD studies, there is a lot of polycrystalline phases.
Right. We have a very polycrystalline phases. And for thermal treatment, after the spin coating, usually we heat it in the oven. And probably we need to change the temperature of the oven to see the difference with the heating temperature. And also between the step when we spin coat it, we dry the sample. This also is important.
Yeah, the time is also important, I think, isn't it?
Yes, sure. I mean, there are many things to be improved, like the interface, maybe by etching layer and surface treatment. I mean, for surface treatment and heating also need to be studied. And maybe we need to put intrinsic layer between zinc oxide and cuprous, like PIN to make.
Yeah, I see. You just make about just buffer layers. As a result of that one, you can easily just eliminate the effect of the diffusion of the copper from upper size to lower size. So that's going to be just because we are working the same, not the same subject, but the same materials.
Okay.
So we are going to just know the details because those optimization is very important. It depends on the time and the thermal treatment case.
Right. Yeah, we need to do some more research on it.
Yeah, because another question is going to be just the silver is used. The silver is you are saying that silver makes a good ohmic contacts.
We use silver past.
Yeah, past, but in any way, just you are making just the silver, and you are saying that there is a silver, there is a ketone structure. That ketone is easily be diffused through the structure. So you can easily be just talk about if there is just ohmic contact behavior. That ohmic contact behavior is going to be just because of the solution is going to be just diffused inside. All right, so. It is not so easy because instead of those pasta case, you have to just use the evaporation case. Evaporate those silver from just the physical vapor deposition techniques.
We can use this thermal. We have a thermal evaporator. We can use the thermal evaporator for top contacts.
Yeah, that is going to be better because otherwise it's not easy to eliminate the interface or the other one produced by the solution of or the pasta.
Sometimes we tried the operation for another research, but we didn't get good result. Silver was better. That's why we continue with this.
I see, I see. After that contact, the metal contact, you can easily just apply that silver pasta because you can easily just eliminate that diffusion through the structure. That is why I'm asking.
Yeah, I think we need to think about the contact as well. Yeah, this is important point. Thank you.
All right. Thank you very much again.
Thank
I
you.
think there is no other questions. So take care and see you next time.
Thank you. Thank you very much.
Bye.
Bye-bye.
Bye. So I would like to say that this is the end of just the Team Films talk for today. So the next time is going to be just about Team Film solar cells for the second part is going to be just start at the 11 o'clock. So we can easily just treat that time. There is about, you may use that time as what coffee breaks and the other break time. As a result of that one, you are going to start at 11 o'clock by the what? With just the Görkem Günbaş is going to be just the chair of that talk. Team Film solar cell for the second part. See you, bye. I would like to thank